Hello and thank you everyone for attending today's webinar, Diagnosing Coupling Failure, the simple steps you can take to identify and fix coupling failure, brought to you by Design World Magazine and Ruland. We'd like to thank our presenter, Bobby Watkins, for being here today. I'm Mike Santora, Associate Editor for Design World Magazine and couplingtips.com, and I'll be your moderator. Just a couple of housekeeping details before we get started. You'll see several boxes on your desktop, all of which can be moved around to suit your preferences. Initially, the Q&A box is at the lower left, but this is where you'll enter your questions for the Q&A session. Another box to note is the additional resources, initially at the lower right-hand corner of your desktop. These resources are for your information needs. We also have a tweet box right on the desktop, so feel free to tweet any interesting points right from there. There's a list of hashtags for to use. And lastly, we are showing a video today, so to ensure they stream properly on your console, close any extra windows and applications using bandwidth. Bobby Watkins joined Ruland in 2003 as the Vice President of Sales. He has extensive mechanical application experience and assists engineers around the world spec the right coupling for their design. Prior to joining Ruland, Bobby worked for THK as a district sales manager with responsibility for strategic accounts, sales management, and employee development. He also has extensive industrial distribution experience with Cayman and Atlantic Tracy. Bobby has over 30 years of sales and sales management experience, industrial distribution, and mechanical component manufacturing. He has in-depth understanding and knowledge of the international markets and customers through his global sales responsibilities. And so, without further ado, here's Bobby Watkins.
Hi, Mike. Thank you very much, and thank you all for attending today's webinar, and I hope some useful information comes across for you. So the slide here is our webinar agenda. We're going to review the different types of zero backlash couplings, typical Ruland applications, the 12 most common errors in coupling selection, installation overview, ways to identify failure by coupling style or type, and how to avoid coupling failure in the future. This slide, if you would please, is a poll question. And again, it's asking if you'd experienced a coupling failure in the last 6 months, and it's a yes or no. And if you could please answer that question, we would appreciate it. All right. Now, the types of couplings that we're going to discuss today. The flexible types of couplings: beam, bellows, disc, curved jaw, Oldham, and then not a flexible type, but a very important coupling to consider dependent upon your application is the rigid type couplings. Here's a very typical application for our motion control couplings or our rigid couplings. This is a ball screw actuator driven by a stepper or a servo motor. And as you can see, there's a beam coupling connecting the motor to the actuator input shaft. Common industries: printing, packaging, semiconductor, solar, medical, food processing. The applications for an actuator of this type are almost endless. They're showing up in almost every industry. And this is an extremely common configuration for a linear actuator with a motor bracket and a coupling connecting. The 12 most common errors in coupling selection. Number one is torque. Maybe not understanding the torque required of the application, or not understanding the torque capability of the coupling that you've chosen. That's another possible way to make an error in picking a coupling based on torque. Speed. These different couplings have different speed ratings, and you want to be very careful not to drive a 4,500 RPM rated coupling up at 6,000 or 7,000 RPM. So Double checking the speed capability of the type of coupling you're using is very important. Inertia. These drives tend to be very, very sensitive to inertia. A lot of these are very small stepper or servo motors. And for example, a very heavy stainless steel beam coupling and a very light duty application can cause inertia issues. It can cause you to trip out your motor. So again, the weight of the coupling itself is a factor. The duty cycle, how many cycles do you plan to use the coupling for? What is the projected life you'd like to see out of your system? Number 5 is dampening or cushioning, if you will. Deciding up front whether you need a coupling that has some shock absorption to protect your components, or if you've got an application that requires very high torsional stiffness, and that's going to decide whether you want a dampening type coupling or a high torsional stiffness coupling. And again, number 6, selecting the wrong coupling for the application. And again, any of the factors that we're going to talk about can go into leading you down the wrong road and choosing the wrong type of coupling. And we'll review the factors. Number 7, wind up. Again, wind up is, we'll cover that a little later in a few more slides what wind up is. But again, it's a factor, and wind up can cause positioning error. Again, it's another factor to be considered. Electrical isolation. Some applications require electrical isolation, and this isolation many times is provided by the coupling. And again, is this a feature that you need? And this needs to be taken into consideration in your coupling choice. Fail-safe design versus a fuse-type coupling. And again, this depends on your application. A lot of times, whether it's a Z-axis, but again, certain types of couplings are fail-safe, so that if something were to happen for a spider coupling, for example, the spider will fail, but you'll lock up jaw to jaw on the hubs, and you'll still be transmitting torque. And some are designed as a fuse-type coupling where they'll break and you'll disconnect. And again, deciding up front whether you need a fail-safe design or you'd prefer to have a fuse-type coupling is important. Misalignment. The degree of misalignment that you need for your application is very, very important. These different types of couplings have different misalignment capabilities, and we'll review that again. If you need a lot of parallel misalignment, for example, an Oldham coupling might be a good place to look. Environmental conditions, temperature, outgassing. Certain types of these couplings will outgas the spider couplings. The spider itself will outgas. And again, this is an important consideration to know whether or not you need a coupling that will outgas or not. And again, part of the environmental condition questions that you need to ask. Selection too late in the design process. This is really common, and I'll give you a couple of examples of couplings being selected too late in the design process and causing issues. For example, if you know up front that the coupling you require is going to be an element type coupling, a spider coupling with a spider, or an Oldham coupling with an Oldham disc in the middle, you need to accommodate space between your shaft ends to allow a space for the spider or the Oldham disc to sit. And we run into applications all the time where the design's done, the shafts are very close together, but they need an element type coupling and the room isn't there, and you end up having to move things around to accommodate. So it's nice to have that information up front before you finalize your design. Another very common error that we see is on a motor bracket type actuator like we saw in the previous slide. These motor brackets have a space for the coupling to sit in, and a lot of times we'll see that that space for the coupling in the motor bracket is too small for the coupling required. So again, taking the coupling that you're going to use into consideration before you pick your motor bracket and before you set the distance apart on your shaft ends can save you a lot of headaches in the long run. Torque. Again, we talked about this being one of the common errors. The difference between steady state and max torque, derating torque capacity based on motion type for beam, bellows, and disc couplings, understanding how couplings are rated. Oldhams have a brake torque, for example, and jaws have a peak torque. Rigids have a superior torque capability but do not allow for misalignment. So certain types of couplings, beam type, bellows type, disc type. If you look at our coupling ratings, you'll see a static torque rating and then a note that says, for single direction application, divide the static torque by 2. And if you are reversing, divide the static torque by 4. And these are your design numbers that you need to use when you're picking your coupling. Again, certain types of couplings, whether it's reversing or single direction, it doesn't affect the torque capacity. Oldhams are like that, and jaw couplings are like that. So on the Oldhams and jaws, you'll see what we call a rated torque. You don't have to use a formula of divide 2 or divide by 4. These designs of couplings, the Oldham and the jaws, they're rated the same for reversing or single direction. And again, it's important to note when you're choosing the coupling type that you look, is this a rated torque and I have to derate from there? Or is this, I'm sorry, a static torque and I have to derate from there? Or is it a rated torque where I can use this number, reversing or not? So let's move on. Torque failure. Here's a picture of a torque failure for a bellows coupling. As you can see, the bellows in the middle is deformed quite a bit. If this coupling were to remain in service for much longer, that bellows would actually tear. It would tear, and you would end up with that coupling in 2 pieces, part of the bellows attached to one hub, part of the bellows attached to the other, and a clean rip through the middle of that coupling. Just a note, because of the design of bellows couplings, that bellows in the middle is thin stainless steel tubing, and when it does start to fail, a lot of times a crack will develop in the bellows, and you can hear it in operation, and it'll make a snap, crackle, pop kind of noise as that crack in the bellows opens and closes. So if you've got an application for a bellows coupling and someone says it's making cracking noises, it's making popping noises, it's near the end of its service life, and it's time to order a new one because it probably won't last much longer in service. So here's a torque failure for a beam type coupling. And again, there's jagged edges. You can see pieces of the beam coupling itself have broken off. And this will be usually a sudden failure with probably not a lot of noise and a lot of warning. These, typically the failure will take you by surprise, if you will. Speed. The failure most often occurs when maximum speed is exceeded. How Ruland determines speed ratings. Again, we mentioned the fact that the different types of couplings have different maximum speed ratings, and the importance of having a balanced design at higher RPM. And we'll show some examples of this in the slides that are coming up. Here's an application. We have a printer. We have a printing application here. And they had an issue with banding, print error, if you will, and vibration in the system caused by the coupling, causing the printer to band the printing and have errors in the printing caused by vibration. All Ruland flexible couplings are of a balanced design. So, and there are couplings out there that do not have a balanced design. This is one of the applications where you can get into trouble just because you haven't used a balanced design. the coupling is inducing vibration into the system, in this case, the printer, and you have an actual error in printing and banding of the printing. Inertia. Again, we talked about servo coupling inertia determined by mass and distribution about the axis. Too much coupling inertia, especially in systems with intermittent starts and stops, can introduce resonance into the system, causing premature failure and or poor system performance. The standard material in all of our flexible couplings for the hubs is aluminum. And again, to keep the weight down, to keep the inertia low. A common scenario where customers will get in trouble with inertia is on beam coupling applications, where they've got an application and they're using an aluminum beam coupling, and the torque capacity is not what they need. It's too low. They're having issues with wind up because the aluminum beam coupling just isn't strong enough, and they're ending up with positioning error. So many times people will say, we'll go to the stainless version. We don't have enough room to put a bigger coupling in. We're going to just go to the stainless steel version of a beam coupling, which does have higher torque capacity, and that's going to solve our problem. Well, again, stainless steel beam couplings are much heavier than the aluminum versions, and it wouldn't be unusual at all to switch from an aluminum beam coupling, go to a stainless beam coupling, and now you've got issues with too much inertia. Your servo or stepper motors are tripping out. And again, this is an example of inertia causing issues and being a factor in your designs. And again, here's the picture of the aluminum versus the stainless steel beam coupling. And again, the stainless steel version of the same diameter and length is much, much heavier than the aluminum version. Again, something to be careful of. Many times, if you're using an aluminum beam coupling and it does not have enough torque capacity, many times a better option is to go to a different type of coupling to solve the problem versus going to the much heavier stainless beam coupling. There are better options than just switching to a stainless beam. Duty cycle, the types of motion, continuous, start-stop, reversing, and again, we talked about certain types of couplings, the beam types, the bellows types, the disc types. You have to take that rated, static torque number, take this into consideration, your type of motion, and derate it. How often is the system running? There's always a consideration. Failures often occur when the type of motion is not accounted for or when number of cycles is not understood. And again, I'll give you an example. Indexing. You know, you've got an application where you're indexing, the coupling is not actually making a full rotation, but it could be indexing at a high rate. And this is, again, pretty stressful on a coupling, and it's not going to last forever just because you're not rotating it at higher RPMs. And again, this is just an example of the duty cycle that you have and the motion profile that you've got. And again, here's a duty cycle application with jaw coupling. So you've got a hard start, a very aggressive move profile. And again, for that type of an application with a very aggressive move profile, a curved jaw coupling is a good choice. Typically, it will protect your bearings in your motor, protect the bearings in your actuator from that shock, and it will extend your component life. And again, if you've got a gradual start-stop application, slowly coming to a stop or reversing, at that point, a beam coupling might be fine, an Oldham coupling might be fine. And again, the aggressiveness of your move profile is definitely a factor in choosing whether you want to use a jaw coupling or something different. Dampening. Dampening, shock absorption, if you will. The jaw coupling, again, is excellent for this type of an application. It shock loads, it's cushioning the shock loads. And again, failure occurs when this is not accounted for in the design and the wrong type of coupling is used. The coupling example at the bottom of the picture being the wrong type of coupling for a very aggressive move profile is a beam coupling that don't tend to work as well. Bellows couplings, again, don't have any dampening characteristics to them. And if you're too aggressive with your starts and stops, you're going to have issues using bellows couplings and beam couplings. You're going to have to take that into consideration. And here's a dampening application example. You've got a food processing OEM who's got hard start, hard stop, aggressive move profile, used a spider that was too stiff and would prematurely lose elasticity, tested a softer spider which eliminated the premature failure and had no negative impact on system performance. So our curved jaw couplings in most sizes have 3 choices of spider hardness, and again, taking into consideration how much dampening you need will help point the right direction as to what spider to use. So I use the 85 durometer blue, the 92 durometer yellow, or the 98 durometer red. Selecting the wrong coupling for the application. Most fully understand all parameters of the application prior to the selection. Selection should be considered early in the process. Many servo couplings exist. Knowing the pros and cons of each one is critical to selecting the correct one. And again, here's an example of a rigid coupling. And where this would be definitely a wrong choice would be any system design that had to accommodate misalignment between the shafts would be a bad choice for a rigid because they will not accommodate any misalignment. And if you do use a rigid coupling in an application where misalignment is present, you're going to have premature bearing failure, bearing failure on both your motor and your actuator. So again, it's an example of, choosing the right coupling right out of the gate. And again, here's an example of using the wrong type of coupling. A mixer OEM is using a bellows coupling to connect a motor to the paddle and experience failures within a few hours of running. Bellows couplings require close bearing support on both sides to properly function. Solution was to use a rigid coupling, which is suitable for unsupported applications. All of the flexible coupling designs require bearing support on both sides. So typical of the picture that we showed you with the ball screw actuator, the motor has a support bearing on the output shaft of the motor. The input shaft of the actuator, the ball screw actuator, has bearing support on it. There's an application example where good bearing support. And we do run into applications where customers will make a design and only have a bearing on one side. And you cannot use a flexible coupling in a design that has a bearing on one side only. The only coupling that has a possibility of working with bearing support on one side only is a rigid coupling. And again, even at that, should review the application just to be sure. Wind up. Talked a little bit earlier about wind up. Wind up is often confused with backlash, and they are not the same. Backlash refers to power transmission error, while wind up is position error without torque error. All couplings have wind up, and a wind up failure occurs when a coupling with too much or too little wind up is selected. So backlash is actual clearance in the coupling itself, where there's space between the spider and the jaws. In a jaw-type coupling, for example, there's actually clearance there, which is error. Ruland only makes zero backlash couplings, so, but some couplings do have wind-up or cushioning, if you will. And a good example is the spider couplings with the spider of the different hardnesses of material. There's no error. There's no space between the spider and the hubs of the jaw, but it does dampen, it does compress, and that is wind up. It's not an error. You wind up a spider coupling, or one of our spider couplings, a zero backlash spider coupling. You wind up that spider, it compresses, it rebounds, retains the torque, and again, that is not an error. It's dampening or cushioning, if you will. Wind-up application example, an inspection system, and the OEM selected a 4-beam coupling to move an eye, optical inspection, if you will, over short increments. A 4-beam coupling was not stiff enough to accommodate the short movement, and positioning was slightly off, leading to poor system performance. This is where the coupling wound up like a spring, if you will, and you get a momentary positional error when the coupling does that. So this was an application where wind-up was causing a problem, and they needed a coupling that had higher torsional stiffness. And in this case, we're showing the example of going from a beam coupling to a double disc type coupling to increase the stiffness, decrease the wind-up, and give them the accuracy that they needed. Electrical isolation. Electrical isolation is used to separate drive and driven components to prevent extraneous electrical currents from being passed between them. Specifying the wrong coupling or not understanding how a specific coupling fails can lead to electrical currents inadvertently being passed between components. This is, you see electrical isolation mostly in encoder and instrumentation applications where you're getting feedback off of the drive system to an encoder, and any stray electrical current in an all-metal coupling could stray out of the drive system, the motor side, and throw the readings off on an encoder, for example, or a meter, some type of instrumentation. This is typically where, and at least in our applications, where we see the need for electrical isolation. And these are some of the designs that have some level of electrical isolation. Jaw couplings, when installed properly, this is a coupling that can be used for electrical isolation. Oldham type couplings, which is the middle picture, this can be used, that's a possibility. And then disc type couplings, we do offer a disc type coupling, a double disc type coupling with a non-metallic center assembly to isolate the coupling hubs from one to another. And these are just some of the options if electrical isolation is an important component in your application. Fail-safe versus a fuse-type coupling. Understanding how a coupling may fail is critical during the design process. Oldham couplings are a fuse-type coupling, and power transmission will stop upon failure. A jaw-type coupling are fail-safe as the tenons will interlock and continue power transmission. So again, depending upon your application, you may want a fuse-type coupling, and I'll give you an example. You've got a process where if something gets jammed in the machine, maybe it's letters, maybe it's a sorter, and there's a mechanical jam up in the machine. In many cases, you want the coupling to break, or in this case, we're talking about an Oldham in particular, that disc to break and disconnect power transmission. Stop. And this can protect the drive systems from the machine from further damage. A jaw-type coupling, spider-type coupling, if the spider fails, the jaws on a jaw coupling will interconnect and you'll still drive. You'll still have power transmission. And that can be advantageous, and I'll use an example, in the semiconductor industry, in wafer manufacturing. In a Z-axis, you're lifting a boat of these wafers, which are tremendously expensive. And in the case of a drive system, a failure of some type, they do not want that coupling to fail. If the spider fails, they want the jaws to interconnect so that they don't backdrive their system and drop a load or a boat of wafers or something valuable. So again, a lot of times you'll see the need for a fail-safe coupling where you continue to be connected in Z-axis applications where if the coupling was to fail, there's enough weight or mass to backdrive the system and drop a load. And again, just another consideration in the difference between a fail-safe and a fuse-type coupling. And here's an example of a single direction conveyor line with repeated starts and stop. They wanted a coupling to continue with power after a transmission, power transmission after a failure. A wafer handling manufacturer needed a coupling that completely stops power upon failure. So again, these are just a couple of examples of, do you want a fail-safe coupling? Do you not want a fail-safe coupling? And it's an important part of the design consideration up front. Why misalignment is a concern, and my goodness, something very bad happened to that beam coupling in the picture. So misalignment is a concern. Not properly accounting for it can lead to premature coupling or system component failure, introduces RPM limitations, vibration, and noise, potential for damage or injury. Most systems are going to have some type of misalignment, and we'll talk about that in the next slide. Some of the common causes of misalignment, parts from different manufacturers, different coupling, different motor, different lead screw, inaccuracies in system assembly, mounts introduce misalignment, excuse me, system motor movement during operation, system component wear. So there are many, many factors that can cause misalignment, and you have to make sure that you consider all of them to be sure that you pick the coupling that has the right amount and the right type of misalignment compensation that you're looking for. These are the types of misalignment here. Angular misalignment, if you've got an application where relatively speaking, you have a large degree of angular misalignment, a beam coupling might be a good choice. To the right is parallel misalignment. Shafts are offset, if you will. And if you've got a large amount of parallel misalignment to consider, an Oldham coupling could very well be a good choice. Complex misalignment, bottom left. This is a combination of angular and parallel. And again, identifying the amount of misalignment in that complex misalignment application, again, it can lead you to choose the right coupling that's going to have the right amount of angular and the right amount of parallel to accommodate that complex misalignment that you need to address. Axial misalignment. Axial misalignment, the shafts moving apart or in toward each other, is typically caused by thermal expansion of motor shafts. Motors heat up during use, and the motor output shafts elongate due to thermal increase. And choosing the right coupling that has axial misalignment to accommodate thermal expansion of your motor shaft is important. Most of the flexible couplings do accommodate some axial misalignment, but rigid couplings do not accommodate axial misalignment. So again, if you've got a high-speed motor, and the higher speed motors tend to have more axial elongation of the shaft than the lower speed motors, it's something to watch out for, especially if you decide you want to use a rigid coupling. You want to be sure that you have minimal thermal expansion of your motor shaft, minimal if any, because the rigid won't accommodate that. Ways to evaluate shaft misalignment. A scale, good enough when installing, do not require high precision. This is good for like a beam coupling or an Oldham coupling. Dial indicators, generally good enough for use with servo couplings, but time consuming. Laser alignment systems, highest level of accuracy, can be quicker than a dial indicator system, but at a significantly higher cost. So if you're using beam couplings, if you're using Oldham couplings, typically a good scale is fine. If you're using bellows couplings, disc couplings, rigid couplings, if you're using them occasionally, dial indicators is probably the most practical way to ensure that your shafts are aligned. If you're in volume and you're building large quantity of machines and installing large numbers of rigid couplings, bellows couplings, disc couplings, it's probably a good idea to invest in a laser alignment system at that point to ensure you've got your shafts aligned properly. Again, addressing misalignment, best addressed during system design and testing. Be sure that mounts are secure and designed from sturdy material. There is a significant system misalignment. If there is a significant system misalignment, a rigid coupling can be used to align shafts in some cases. The second bullet point, be sure that mounts are secure and designed from sturdy material. The most common problem we see from this is encoders. A lot of encoders are mounted on a flimsy bent sheet metal bracket, which move while the machine's running. They vibrate. They're not robust enough. So this is an example of sturdy material used for mounts. And again, encoders, you see it most often. Encoders are light. They don't weigh a lot. A lot of thought's not given into the fact that the bracket's going to vibrate, and you can have coupling failures due to vibration of the bracket, which is actually moving the encoder and moving the coupling. So that's one of the big culprits with sturdy material is encoder brackets. Beef up those encoder brackets, and you'll save yourself a lot of headaches. And now we're going to show a video clip on how you can use a rigid coupling to align shafts.
Today, I'm going to be showing you how to use a rigid coupling in order to align components in preparation for the use of a flexible coupling. You can see, here we have a movable component with extremely high angular and parallel misalignment. The entire fixture is currently loose. First, we'll take our two-piece rigid coupling and partially assemble it onto the motor. We'll work to align our second component such that the shaft can also go into the coupling. Then we'll begin the installation of the rigid coupling per the instructions that can be found at Ruland.com. The rigid is now fully assembled, and as you can see, the parallel and angular misalignment that we had present in the system before is now fixed due to the alignment of the rigid coupling. Now what I'll do is go through and begin to tighten down all of my fixtures. Now that all the fixturing is tightened down, the system is aligned by the rigid coupling. So, we'll remove the rigid, and the system is now prepared for the installation of a double disc coupling. For installation instructions for disc couplings, please see our video series at Ruland.com. Now that the disc coupling is installed, it's ready for use.
All right. Hopefully that video was helpful. This next slide, we have another poll question, and if you'd be so kind as to fill out the question, we would sure appreciate it. All right. Again, thank you for filling out the poll question, everyone. Environmental considerations. We've got temperature, we've got moisture, we've got chemicals, and vacuum. These all need to be taken into consideration when picking the coupling. Example number one, aerospace customer using a coupling to control aperture on a telescope. Need a coupling that can survive vibration of takeoff, vacuum of space, extreme temps, and cannot outgas. And again, our solution for this application was an Oldham coupling with stainless hubs and a PEEK insert, which is a special material, if you will, that we use on our Oldham couplings that has extreme temp capability and does not outgas. Number 2, medical customer requires a coupling in an autoclave. Need coupling that can survive high temperatures for short intervals. Originally selected a bellows coupling but failed due to epoxy. Our bellows couplings, by the way, are epoxied together, so if you do exceed the temperature limit, you will soften the epoxy. You'll get a coupling failure, you will. And again, an Oldham with a peak disc was a good choice for this solution as well. Selecting coupling too late in the design process, and that poor goldfish on the right. Anyway, if left until the last design component, the system will have restrictions that limit choice. And again, the envelope, the length of the OD, your coupling may not have the desired performance, could require an expensive coupling custom to be specified. And again, this is going back to, did you leave the proper distance between your shaft ends to accommodate an Oldham or a jaw coupling spider, or an Oldham disc? And on these motor brackets, in the initial picture we showed of a typical application with a motor bracket hooked up to a linear actuator, is there enough room inside that motor bracket for the proper coupling? Again, just an example. Selection timing example. So a fluid dispensing OEM designed a system, including mounts, before specifying a coupling. The only coupling that would fit was a single disc coupling, which has no accommodation for parallel misalignment. Mounts are not rigid enough to support the operation of the system and would cause parallel misalignment. Too expensive to redesign the system, and no special alternative was suitable, leaving the OEM to accept shorter than average service life. And again, if you didn't leave enough room between your shaft ends or enough OD and length space, you might have to settle for a coupling that's not ideal for the application and have to live with the shorter life. And again, no one wants to do that. So again, it shows the importance of selecting the coupling before finalizing your motor bracket and finalizing your distance between shaft ends as part of your design. Installation overview. Even if a coupling is properly selected, poor installation can cause failures. Again, staying within the recommended misalignment ratings of that coupling at installation is critical. So during this section, we will cover each type of coupling and what to be careful of during installation. And we do have full instructions at Ruland.com, full instruction videos on installing couplings. So it's a good resource. Always be sure coupling is used within our ratings. Use a torque wrench for proper screw seating torque. Common required tools for installation, torque wrench. It's really important to use a torque wrench when you're tightening screws on couplings. It's an overlooked piece of information, if you will, but over-torquing or under-torquing the screws on couplings is going to greatly affect how well they clamp, how long they last. Please use a torque wrench when you're installing the couplings and use the appropriate torque setting for each size screw, and we have that listed on our website as well. Shim stock or feeler gauge, shaft alignment measurement tool, such as a dial indicator system or a laser alignment system. Rigid couplings, be sure to install screws starting with the inside 2 or 4, depending on the style. So here's an example. This is a 4-screw version that we're looking at, and the way this coupling should be installed is the 2 inner screws should be tightened to 50% of the total torque you're going to tighten the screws to. Go out to the outer screws, bring those up to 50% of the torque. Go back in, bring the 2 inside screws up to 100%, and then go to the outside screws and bring them up to 100%. That sequence of tightening those screws is very important. Beam couplings, tighten one hub first, and before tightening the second one, rotate the coupling by hand to allow it to reach its free length. Certain couplings are prone to be installed either compressed or extended. This being beam couplings and bellows couplings seem to have the biggest issue with this. It's very important not to install these couplings either compressed or extended. It drastically reduces the life of the service life of the coupling if it's not installed at the correct length. Oldham couplings slide hubs onto the shafts with tenons at 90 degrees before inserting the center disc, but do not tighten. Place disc on one hub and center by hand. Use a shim the thickness of the coupling's axial misalignment rating. Slide the second hub into the groove until the tenons touch the shim. Tighten both hubs and remove the shim. Again, Oldham couplings have a disc, and that disc actually moves up and down, if you will, if in this case, to accommodate the misalignment. And there needs to be a gap or space, if you will, to allow the disc to move. If you were to assemble this and squeeze the hubs together and tighten the hubs down, you've trapped the disc at that point, which you don't want to do, which is why we talk about shimming and leaving a gap between the face of the Oldham disc and the tenons on the coupling hub. And again, here's a small gap in this picture showing the clearance, if you will, and the gap that is required for proper installation and for you to, receive the proper life out of the coupling. Disc or bellows coupling, again, this is another one that it's critical that you install it not compressed, not extended, but at the proper length. Tighten one hub first before tightening the second one. Rotate the coupling by hand to allow it to reach its free length, and then tighten the second hub. Jaw couplings. For small sizes, slide hubs onto shafts with tenons facing each other. Fully tighten the screws on one hub. Do not attempt to press standoffs into the balance holes. We'll talk about that in a second. Insert jaws of second hub into spider openings until standoffs contact the second hub. It may require some force to press the second hub into the spider. This is common. Ruland jaw couplings are curved jaw, zero backlash couplings. It is a press fit on the spider. These do not go together easily, and that's intentional. And there needs to be a compression fit, if you will, to maintain zero backlash, so there is no clearance, so there is no error. Larger sizes, you might have to use a press to put them together. And again, if you look at the face of the hub in the picture, there's a standoff on the spider, a nub, if you will, which is an installation aid. And when you look at our hubs, you're going to see these holes in the face of the hub. These are balanced holes. These hubs, like all of our motion control hubs, are a balanced design. So those are balance holes to offset the hardware. They are not meant to have the standoffs on the spider be pushed into them. And again, like the Oldham, there's a proper engagement, depth of engagement required with the jaw coupling. In the picture, you can see standoff touching hub. This is that nub I was talking about. And that is not a hard mechanical stop, by the way, that standoff. It's a visual aid. So you want to watch as you push the coupling together until that standoff just touches the face of the hub. Now you're at the proper insertion depth. And again, it's not a hard mechanical stop. You could actually keep compressing the coupling, squash that standoff down, if you will, and over-insert the coupling hubs together. and have problems. So again, that standoff is not a hard mechanical stop. It's a visual aid so that you can see when you're at the proper depth of insertion and you've got a gap. If you can see the gap between at the top of between the face of one hub and the jaw of the other, and this gap is proper. All right, this is a video.
To install the jaw coupling, we're going to need a feeler gauge which is set to the correct size, 2 hubs and a single spider, and a compression device. Place the semi-assembled jaw coupling into the compression device and tighten until the nubs on the spider are touching the base of the hubs. Use the feeler gauge to maintain the gap between the hubs to prevent metal-to-metal contact.
All right, how different couplings fail. Here we've got a beam coupling torque failure, where you've got rougher jagged edges where the break occurred in the middle of the beams. And again, this is typical of a torque failure on a beam coupling where you have these rough jagged edges. Here's a beam coupling that failed from misalignment. You don't tend to have those jagged edges. It tends to be at the start of the very first beam, as circled in the picture. And typically that will have a clean edge break, and that is typically a misalignment failure. A bellows coupling torque failure, again, well, I think we saw this slide earlier, and again, a lot of times when you do have torque failure on a bellows coupling, it'll actually be in 2 pieces, and that bellows a lot of time is just torn in 2. Here's a misalignment failure on a bellows. Again, toward the end, the first rib of bellow, if you will, you can see the break. And if it's toward the end, right near the hub on a bellows coupling, that's where the break occurred, typically misalignment failure. Disc coupling failure. Disc couplings are built with shims or disc springs, if you will, thin laminations of stainless steel. And they're riveted or screwed in between the hubs, and this gives you some flexibility. Over time, where the rivet goes through the disc or the screw goes through the disc, that hole will oval out, if you will, and you'll start to get some error in a disc coupling, because it's starting to have some clearance where the screw holes or rivet holes have ovaled out. So a lot of times you have a disc coupling failure of clearance building up and having error in your system. Jaw coupling failure. Here's a spider which is disintegrated pretty badly, but misalignment and torque will look the same. Deformation of the spider leads to loss of zero backlash. You need to calculate the number of cycles to determine how early in the coupling's life it failed. If low cycles, it's most likely torque. So again, when the spider loses its ability to rebound from being compressed, you're going to start to develop some clearance at that point. And this is actually a normal process over time. The spider coupling spiders, the Oldham coupling discs, they're wearing elements. They were not designed to last forever. So again, you need to set up a maintenance schedule to change out spiders and spider couplings, change out discs and Oldham couplings on, a regular interval to maintain zero backlash and, maintain the integrity of your design. Oldham coupling failure. You can see the disc has broken. Pieces are laying down the bottom. and the top pieces will fall out and you will disconnect. So this is a fuse. This is an Oldham coupling where the disc has broken. And this could be intentional because there was an overload in the machine. The Oldham coupling did its job, what you wanted it to do, the disc broke, instead of doing further damage to the machine downstream. Rigid coupling failure, almost due to misalignment in the system, and the coupling will break in the cross cut. Again, if you have misalignment present in your system and you've used a rigid coupling, many times you'll see this break. The coupling will break this way. Another thing that you might see is bearing failure as well. The coupling's held up, but you've overstressed the bearings on either side of it, and you've destroyed your motor or destroyed your gearbox, or in some cases both. So again, rigid couplings, if you get a failure on a rigid coupling, it's almost always due to some misalignment present, which the rigid can't accommodate, and you're going to have major problems. Avoiding future coupling failure. How to avoid coupling failure. Here's a chart that shows different types of couplings, beam type, bellows type, disc type, jaw type, Oldhams, and it gives you an idea of the amount of forgiveness for misalignment each one will give you, angular, parallel misalignment. So it's a quick visual chart that gives you an idea how forgiving the different types are, gives you an RPM rating, and so forth. Coupling selection guide. This is a chart which is going to show you quickly, it's just a visual, what type of couplings are dampening type, cushioning type, if you will. What types of couplings are torsionally stiff. And again, it's just a little visual chart to show the different types and how they fall into comparison with other types as far as torsional stiffness and so forth. Why Ruland? A little bit about us. So we're just outside Boston. Everything we make is right here in the building. We're the only North American manufacturer to offer all 6 types of servo couplings. It's a huge deal. You give us an application, we're going to come back with an unbiased opinion as to what type of coupling to use because we make them all. So it's an important factor in design that you've got all the choices open to you, and you're going to get application advice that's not bent toward a jaw coupling or trying to make a beam coupling work when something else would work better. We've got them all. And again, all products are manufactured in Massachusetts. Very quick turnaround times. All of our flexible couplings have a balanced design as standard. And again, we've got website live chat technical support. We've got great information on our website. So please use this as a resource. And again, a poll question here. If you could fill that out, that would be fantastic. Questions. So this is the question section, and hopefully we have some.
Okay, thanks, Bobby. Like Bobby just mentioned, we are now open for questions. We do have, we're running short on time, but we do have a few that I think we're going to be able to get to. So, Bobby, the first question we have is, I'm trying to replace a jaw coupling spider. Can I mix manufacturer hubs and spiders?
It's a good question. It's a very common question that we get. No, you cannot. Ruland, typical of jaw coupling manufacturers around the world, our spiders fit our hubs only. So spiders and inserts from different manufacturers do not interchange from one to the other. If you have a Ruland coupling spider failure, you need to replace it with a Ruland. It's the only thing that will fit.
Okay, Bobby, and we're going to try to field one more question here. Lastly, how much axial force can a beam coupling withstand?
Gotcha. This is another common question. Again, thank you. It really isn't designed to take any axial forces at all. We talked about the fact that flexible couplings are designed to have full bearing support on both sides. And if you've got full bearing support on both sides, there are no axial forces. The bearings are taking the axial force. And if you've got an application where maybe you've got a bearing only on one side and you've got axial forces involved, you really can't use any of our standard designed flexible couplings. They're not meant to take axial forces.
Okay, well, thank you so much, Bobby, for that. I just want to let everybody know that if you have any additional questions, you can refer to the speaker bio box containing contact information for Bobby or myself. And lastly, I want to thank everyone for attending this webinar from Design World. This presentation will be mailed to everyone later today and will also be available at www.designworldonline.com.